Con más de 150 artículos científicos publicados, el profesor OBERHÄNSLI ha desarrollado investigaciones en áreas relacionadas con petrología metamórfica e ígnea, geodinámica y proyectos de cartografía geológica alrededor del mundo. La conferencia del profesor se titula Metamorphic Petrology, a Tool for Geodynamics, Example, Anatolian Belts. Professor OBERHÄNSLI.
So I will give a short review on tools that are used in petrology. I will make a little excursion to petrological modeling, and then I will exemplify what I was trying to show you on the East Anatolian High Plateau. That's actually where the name of orogenic plateau was defined by a man called Strabo roughly 2,000 years ago. Now, index minerals is the petrologic tool that was known throughout the time and is still very valuable. You recognize a mineral in the field and you know exactly where you should be in the PT space. And the index mineral concept is based on the ground truths. But very early on, one could see that there is something else than just index minerals, and these are frozen reactions. Here you see two samples. One sample is the transition from coesite to quartz with the cracks around it, and that was described by Christian Chopin in '84 and was the final proof that continental crust can be subducted. Of course, there were other people that had already recognized that granites or granitic rocks show high pressure minerals and are eclogized, but it was not really accepted. Here I show you the reaction of biotite to plagioclase, and between the biotite and the former plagioclase, a series of minerals were formed, garnet, jadeite, so clear indication of high pressure. At that time, the first personal computers were available and no modeling was possible. So what we did is picking up the rocks, doing structural and textural analysis. We were producing the first age data on separated mineral that we thought would occur together, and finally the whole thing was more or less compiled in a cartoon, and we proposed that continental crust could be subducted. But then the world exploded, IT exploded, and we were able to get lots of computers, databases, and one could add to this fantasy and reaction observation with thermodynamics. If you use thermodynamics, then you can go from petrography to produce grids and pseudosections. Now, here, this is the facies diagram that we proposed for the metamorphic maps, and it just shows the different paragenesis that define some areas within a pressure temperature space that can be connected as facies, metamorphic facies. But all this is based on equilibrium textures and on stability fields. So then the models were, or computer models were available that allowed to go a step further and to include the rock composition in order to produce a reaction grid. Now you can see here that these reactions are moving along these little arrows if the composition of the minerals or the rocks are changing. But principally, this is all stable, static thermodynamics, and you get a grid, and in this grid, finally, you can produce a point and say, my rock has been at a certain time here, and then the rest is fantasy. You put together points in space of P and T. But these thermodynamic models that we are using, they add something that can be further explored. And this is the densities, and one can also access the fluid content of the rocks. Why is this possible? This is possible because when you add rock composition into thermodynamic modeling, you can also calculate the modal composition of your rocks. You can find out how much of which mineral is stable at the point in P and T. And that's what I would like to talk a little bit about in the coming slides. Here you see the problem of the density of rocks. Of course, everybody knows that we have Archimedes density. It's a matter of mass and volume, and a stone, and I call it stone in this diagram, would have a certain density. But realizing that we are working in the lithosphere, we should add some pressure and some heating to Mr. Stone, meaning that we need thermal expansion and we need compression calculated. And the final diagram would look like this. You have a set of different densities growing from 2.5 to 3.3 across this diagram. But this is still very, very schematic. Now, as I said, you can calculate in each and every point of such a grid the composition, not only the stable paragenesis, but also the mode of the stable paragenesis. And if you use the mode and do some more expansion, then you really can get to a density diagram for a rock. Now here is an eclogite, and here is the density diagram calculated through a petrologic stability diagram, as I showed it before, if you want a petrogenetic grid. And you can see that this doesn't look like a very simple distribution of densities. It is very complicated, and densities are low in the very cold areas and in the very hot areas, and you get a density high in the area of high pressure and high temperature. Now, this metamorphic density, as we call it, can be used further if we are going to look at rocks. Here is just an example to show you that, of course, it is dependent on the rock composition. A diagram calculated as the same as the one before, not for the eclogite I was showing, but for a general morp composition taken from literature. And here, the density diagram calculated for a granite. Now, what does this mean? Here is a model taken from literature where you can see the thermomechanical modeling and the respective densities if you assume the physical densities, this simple contouring that I was showing before. We were lucky we could convince these people to redo their model with our metamorphic densities, and you can see that it looks completely different. I go back just to show the differences, and this means that one should not longer ignore the petrology and the reactions that are behind the rocks and the compositions that we are looking at, especially if we are dealing with the crust and the upper mantle. Now, there is further ways to continue and to get from the densities and the rock composition to assess the seismic velocities. Here, two diagrams for the seismic velocity, VP, contoured along the traditional physical density model, and of course, the seismic velocities vary in the same way. But if you take the adapted model with the metamorphic densities, then the seismic velocities are distributed quite differently in space, in P and T space. And the most important fact is that the relation between density and seismic velocity is not anymore linear. Here it looks as it would be a very linear, very simple correlation between density and seismic velocity. And here you can see that it is a very complex, non-linear behavior. So when we are looking for, or when you're trying to interpret geophysical signals, we should remind ourselves that behind this signal there is a rock at the end, and this rock has a density, and this density has not a linear behavior to the seismic velocity. We were trying first to use this for plateau generation, and you can see this is a model calculated with physical densities. We have upper crust, lower crust, and we have the mantle, and it, as a result of the temperature at the asthenosphere-lithosphere boundary, you have an upward force, an uplift force. Everybody knows this. Rifting is uplift due to hot lithospheric mantle. And if you look at these diagrams, you can see that this line here is slightly inclined. It means that the density down here is a little bit lower than the density up here, and that's why we have this buoyant force. But now, my point is, if you are using the metamorphic density model, then you see that it is not possible just because reactions occur. And we were using different rock types. Of course, the composition of the upper crust and the lower crust is not the same, but you can play around as much as you want. You end forcedly with a model that has more layers due to the metamorphic changes that provoke jumps in density. And of course, if we have a jump in density, as I demonstrated before, we have significant changes in wave velocities as they are detected by our colleagues from geophysics. So we have density jumps, we have density profile lines. The densities decrease much faster, so the uplift is higher. And of course, the correlation between these two parameters are much stronger than you would expect from a very simple model. Now I would like to show you this by just using different geotherms. What you see here is a pressure-temperature diagram and geotherms as they are published in the literature for different areas of the world: Northeast Japan, the Aleutians, Southwest Japan. Here is a complicated one for the Andes. And these different geotherms have very significant consequences for the rocks. But which consequences do they have? I must add a little bit. When you do these calculations, the petrological calculations, and you go bring some rocks from the surface down, they release water. Now you can leave this water in your model, or you can do what nature is doing. You can eliminating. What we did in our calculations is we eliminated the water. As you all know, every volcano steams and the water comes up, And we know if subduction would keep the water down in the mantle, after 60 million years, our oceans would be dry. They're still there. Subduction is going on much more than 60 million years. So what I will show you shortly is the influence of different geotherms and on what is going on with the rocks. And I'll focus on subduction zones. And now these are the results for a cold geotherm as we find it in northeast Japan, or as it is published for northeast Japan. Eclogitization is the depths where a crustal rock becomes more dense than the mantle rock. Here is the density of the mantle, and we have different rock types, gabbros, granites, peelites, that are pressurized, brought down along these geotherms, and you see that the gabbro and the basaltic rocks are eclogized at a very high pressure, and if we go back to this, we can detect this about 80 to 90 kilometers depths at 500 degrees. So that's the effect of a cold geotherm. Only gabbros and basalts can be eclogatized and at very deep positions. The Aleutians, so the intermediate geotherm, show something different. Here, gabbros and basalts cross the dry mantle density at a lower level and at higher temperatures. So eclogitization in the Aleutians is at shallower depths, but at slightly higher temperatures. Let's look at the hot geotherm as it is found in southwest Japan. And there you see that both mafic compositions, gabbroic or basaltic, are crossing the dry mantle conditions at even shallower depths, 40 to 50 kilometers. So that's almost crustal depths and at even higher temperatures. And it's always the same rock type that we are using, the same rock composition. It's just the effect of the density changes, so it's not only related to the densities, and it's also related to the PT paths that you are using. And finally, let's look at a flat subduction as it occurs in the Andes. And then you see that, again, gabbro and morb are crossing the dry mantle conditions at relatively shallow depths, so 60 to 70 kilometers, 550 degrees. But here you can see that even aluminous peelites, aluminum-rich peelites, are eclogitizing, this time at very big depths and at higher temperatures. So, in a nutshell, what I was trying to show is that on the one hand, we can calculate from the rock composition using straightforward thermodynamic modeling the changes in density, the reactions, and from there we can go to the seismic velocities. But the changes are not only dependent on the static conditions, they're also dependent on the dynamic conditions. If you use different PT paths, trails, into your diagram, you arrive to the same rock type that you find in the field at different conditions. Now, to bring this a little bit further and looking into the mantle, this is a diagram from our colleagues from Switzerland, Poli. They put all the known reactions into a static diagram, and you see that there are a lot of reactions giving off water during a subduction, even down to pressures of 90 gigapascal, where lawsonite is breaking down and giving up some water. And of course, there is also reactions that we know from the mantle composition, phlogopite potassium richterite, or the amphibole stability field. You see the contouring of the temperatures, and you see this flow line that they use. And here is, of course, in a depth of about 50 to 100 kilometers, you find the melt producing in area that is responsible for the calc-alkaline volcanism. Now, what we try to do is to add to this use this model with the reactions and look at the densities in the mantle. And what you can see here is that we come up with the same section of minerals that give off their volatiles, and then at the very great depths of 200 kilometers, our density model gives this inversion producing some melt. I want to focus on two facts in this diagram. The first one is that there is a density drag force along the downgoing slab. It's more dense on top and below the slab, and then the mantle is lighter on either side. That's one point. And the second point is that this static calculation of densities produces melt down here. It is an ultramafic melt, and the restite or the non-melted portion would be a garnet lursolite. And this area here is far away from what we saw in the further diagram. So this makes you think and not believe anymore in your own modeling. So the first thing that every body is acquainted with is there is nothing like melt in the mantle that does not fractionate. So we added just fractionation in the mantle to our model. And you see immediately density inversion explodes in this area. Still relatively far away from the subduction zone, but it comes up to 50 to 40 kilometers. We come into stability fields where again serpentinites are stable, and we have two types of melts. Melt number one is the ultramafic melt, leaving a garnet lursolite behind, and melt number two is an aluminum-rich melt that has a Harzbergite as a residuum. Now everybody knows there is garnet peridotites, and there is, of course, Harzbergites in this subduction angle mantle. And if you go to the field, then of course you'll find this type of rocks if you look at the right place, and that's a corundum-bearing gabbro. All these crystals here are pure corundum. Unfortunately, it's corundum and not ruby. Also, it's pretty nice. So you see, there is ground truth. These types of rocks are produced, and of course, if they are produced, also exhumed. They're pretty rare. You have to find them, but they exist. Another interesting phenomenon that might be interesting for the geophysics is that if we calculate our densities from the petrology and we add some time to it, the model after about 1 million years after initiation of the subduction looks like this. The slab is still light, is not dense, but it is the mantle below the slab who has already high density, and it is the mantle that is the dragging force that brings down, that initiates the subduction. After 2 million years, you can see that the eclogites have been produced, and that's by far the most dense part of the whole story. And after a certain time, somewhere in between 1 and 2 millions, it changes. The mantle is not the dragging force anymore, but it is the downgoing slab that starts dragging. And this, of course, will have some consequences on where the seismogenic zone is, and should be taken into account when we are interpreting the seismic data. So the state of the art is that we can calculate petrogenetic grids in relation to any rock composition that we give into the models. You see here, there is the rock composition for this specific diagrams. Several people have found out that there is something like a metamorphic density, and we can now calculate from the metamorphic densities our wave velocities. And the quantification of these phenomena, of course, are important in the context of geodynamics, because we can better understand the physical properties and mechanisms of exhumation of rocks. We can understand or interpret the seismic and tomographic results, and it is important for the assessment of the localization of the seismogenic zone. Now, these are the tools, and I would like to bring you to an area where one could work for about 5 or 6 years, and now there is civil war again in the eastern Turkey. This is Lake Van and the Kurdish mountains of the Bitlis. That's the area where Arabia is currently indenting, pushing the Anatolian plate away and pushing the Iranian plate away. So we are talking about this place here where the Arabian plate with force indents, and that's where there is the formation of a high plateau. So this high plateau is not like the one in East Africa. It is there despite the fact that there is no extension, but there is an initiation or an ongoing collision. Now, of course, when we started in this place, the map, there was already a metamorphic map, indicated this is all green schists and amphibolites. We found eclogites, we found blue amphibole, and we found iron magnesium carpholite, which is a high pressure indicator in pelitic rocks. And this is the distribution, so it's not single findings. The whole area, of course, is high pressure metamorphic, bringing us to change the map completely. So all eclogites and blue schists. And what we were able to do is we used laser ablation argon technique, and we could date in some of the rocks, especially in this aluminium-rich rocks. We could date different minerals, especially the micas in situ. And since we did the analysis in situ using non-equilibrium textures, but interpreting the textures in the PT space, we were able to really construct a PT path because we have the ages. We have different paragenesis, paraphyllite, carpholite, it's down here. There's nothing to be dated here. But then we have carpholite chloritoid phengite, number 2, and chlorite phengite and chloritoid phengite, and these were, we were able to date them. So we can really produce PT paths, and we can show that this area is full of low-grade, high-pressure rocks and eclogites. I know I make a big jump, but we compiled the metamorphic rocks from the whole area, and you can see that there is not only one place with high-pressure rocks. No, there is high-pressure rocks here, there is high-pressure rocks here, and there is downgoing slabs. There is high-pressure rocks north of the Bitlis. This is work from Roland from France. So there are a series of blocks. They were all subducting, and the subduction ages are all late Cretaceous, early Eocene. So one after the other blocks between Europe and currently Arabia was subducting under Europe and leaving a series of downgoing slabs and a series of exhumed high-pressure rocks. That was our result of just simple field studies and geology. Now, the models that were published at the same time were studying the same areas, they always, like for example Schönger, put the Bitlis, that's the area where we found the high pressure rocks, on top, and it remains on top. Somehow the slab broke off and that was gone. Modern work does exactly the same. They put Bitlis here, it's in the upper plate, no high pressure, and actually here it should be something like a volcanic arc, and I can assure you that all the metapelites that are blue schist bearing are not typical rocks for a volcanic arc. What I want to focus on is that all the models that were published up to now, they insist on having a mantle plume, heating up the area and being responsible for the high plateau of eastern Anatolia. Having read this, I was of course not happy, but one has to go back to use the geophysical data that is available. It's not much, and this is our results published by geophysicists from the United States, unbiased to the problem whether there is high pressure rocks or not. What we can see, this modern data, 2003, there is, of course, a very thin lithospheric thickness, and the lithospheric thickness is exactly identical to the crustal thickness, so that means there is no lithospheric mantle, and that's the result that comes from this geophysical interpretation. So far, so good. It's still, they didn't care about the high pressure rocks which we find up here. They were just interpreting their geophysical data, which is okay. I then started looking at other geophysical data. For example, the heat flow. If there would be asthenospheric upwelling, no lithospheric mantle there, crust direct on asthenosphere, why should it be cold? You see here, that's the heat flow distribution. That's where it should be hot according to the new geophysical data, and that's the heat flow. Doesn't really fit. Also, the heat flow data is pretty old. If you look at the Boucher anomaly, it's exactly the same. We have a strong negative anomaly. How does this fit with the missing of the lithospheric mantle? So that again then gave us the backup to think again about metamorphic densities. Here is what other people were thinking, what is going on with the water, a model from Lallemand and a model from Diane Darkey. Of course, the downgoing slab is dehydrating, then we have a low density area above this, and of course, the mantle as such is completely hydrated. And a hydrated mantle would be something completely different from an asthenospheric mantle. The rheology is different, and of course, also as a consequence of what I said before, the velocities should be different. So we took this as a motivation and went back to our own work. Here is again the favorite PT diagram. We put in some normal leurzolite with 0.3% of sodium. And what happens is that almost all of the mantle contains minerals that are OH group bearing, like sodium, biotite, stable up to 0.2% in the mode. Here we have chlorite and serpentinite, so up to 10% water can be stored away, and there is only a very little part of the mantle where there is absolutely dry mantle. Now we took a subduction or a path in our PT diagram and did a very strange calculation. I apologize, but it's not easy. We give you a diagram, temperature versus relative humidity. relative humidity means that the mantle here is composed completely of hydroxyl-bearing minerals. So that means fully serpentinized. Doesn't exist, I agree, at the mantle, but that's one of the end members. And the other side is the completely dry leucolitic mantle. And then you can see, of course, that if you are assuming that it is completely serpentinized, at 500 degrees centigrade, the serpentinite breaks down. You can see it here. So you have to change the mineralogy. And just the message from this diagram is that within the first 20% of hydration, there is the big change. You come from yellow to blue. So you change the densities if you hydrate by relatively 25%. That doesn't say how much water is in the mantle, but it says that you have roughly 10 to 20% of hydroxyl-bearing minerals. Now, many of you have seen this type of mantle rocks. Phlogopite-bearing mantle, in any collection you can find this. Hornblende-bearing leucolites, it's available almost everywhere. So that's not something very dramatic. But to leave you with these ugly diagrams, and we go further, we did then the calculation of the wave velocities. And you see, if you add about 10% of hydroxyl minerals to the mantle, your wave velocities drop dramatically. Here, for the VPs, from the 8.1 down to 7.6 or something, and it's the same for the VS velocities from 4.7 down to 4.4. And this is by 10% of relative hydration, meaning if you take an amphibole, 2.3% water in every crystal, that you need about 4 to 5% of amphibole to produce this 10% relative hydration. So there's not much hydrated minerals needed in the mantle to produce a significant drop in wave velocity as calculated by petrology. Now let's go back to what we calculated and compare it to the data that were used by our geophysicists. And you see that for the depths, and this is again GUC, the one I showed before, for the depths where they propose that the MOHO should be 40, they come to a wave velocity of about 4, and we are dropping down to something like 4.2. So there is not a very good coincidence, but the trend is absolutely right. Hydrating the mantle would leave you with the same wave velocities as observed by the geophysicists. Another thing is, of course, when you're adding hydroxyl-bearing minerals to the mantle, you're adding anisotropy. All these minerals, as we know from experiments, are extremely anisotropic. Here, just two examples from Martes: hornblende and clinochlor, extremely anisotropic minerals. And fortunately, the same geophysicists that produced all the other data also gave us a map of anisotropy, seismic anisotropy. And what do we see in the area of study? It is high anisotropy exactly in this area. So that was a further confirmation that we could be on a good trail. So we propose that there is nothing like a direct asthenosphere crust section, but that it would be enough to have a hydrated lithospheric mantle. Here we have 3 subductions, if you remember well, one behind the other. And of course, you could interpret the whole thing, the geophysical data, by adding hydrated mantle here, which would make sense in the vision of a petrologist. But visions are nice, you need ground truths. So the ground truths for this hydrated lithospheric mantle would be that we should find xenolites. There are no available up to now. Maybe somebody finds them. And the rest would be minerals. And as you can see, the minerals are there. Of course, there is hydrated minerals in these rocks. Then I finally convinced a colleague of mine, a geophysicist, to use the same data that were used by the original geophysicists and to do a different type of migration with a much higher resolution. This is preliminary work and it's not very well done. The student, for example, made it the wrong way around, so I had to put it on the head to have depth here. But what you see is that if you migrate exactly the same data with a different model, I'm not a geophysicist, and a higher resolution, you get cold, hot, cold. And this would mean, in my interpretation, yes, there is hydrated mantle. That's exactly where you lower the wave velocities and imply that it is hotter, which is not true. It could be wetter instead of hotter. So the conclusion is metamorphism plays an important role in the change of physical properties of rocks and depends on both the geochemistry of the rocks and the context of the subduction zones. Density changes and the release of water, they control the rheology, the topography, and also, of course, they influence the seismogenic zones. Quantification of these phenomena in the context of dynamic processes is useful to understand physical mechanisms of exhumation, to interpret the tomography differently, and probably also to assess the seismogenic zone. Now, why is this important? I come back as president of IUGS. Why is this important? It is also important because we need to understand and to work together the geophysical data in order to find new resources. Mining is going always deeper. The last big occurrence of copper is Olympic Dam that was been found 1,400 meters below surface, no indication on the surface at all of these mines. It's a joint effort of data mining, data management, it's petrology, all kinds of geophysics, geochemistry. They drilled it and they indeed found this mineralization. So what I think is we have to prepare, and this is a slide from another talk where we are dealing with hazards. We need to change our education and training in order to be prepared for the unpredictable if you think in hazards, but also for the unpredictable if you think in where are the resources to be found at depths. And IUGS has founded a new initiative which is called Resourcing Future Generations. There are from time to time open calls where one can get some seeding money if one has a good idea related to resources right now. And I would like to stress that in 2 years from now, the Canadians are offering a congress called RFG 2018. It's one of the first interims conference between the IGCs that will deal with energy, minerals, water, and the earth as such. And I invite you to think about to be present there, because Colombia is on both, on the resources side as well as on the geodynamic side, a very interesting country. And as far as we have seen up to now, there is a lot of contributions that could come from this country. And with this, I thank you for your attention.
¿Tenemos espacio para preguntas?
Gracias. Yo no sé mucho del tema, pero tengo curiosidad. Esa agua de esos volcanes que todos han dicho, ¿sí le sirve algo para el ser humano? El agua de los volcanes, la parte líquida.
Oh yes, of course. As I said, sorry. Yes, of course it is important. All the waters that are, not the waters, but the volatiles that are coming back through the volcanoes, they were brought down to a big portion by the subduction zones. Of course, there is still primary juvenile devolatilization of the core and mantle going on, but the majority of the gases that are exhumed or that fume out of volcanoes are recycled fluids from the downgoing slab. And as I said, there are calculations, 60 million years of subduction in the style we see it today on our planet would dry out all the oceans. So it is important.
¿Otra pregunta? Muchas gracias, Roland. El Servicio Geológico Colombiano le hace entrega del símbolo del simposio. Sí.